So there's a huge gap between what we think we know about complex systems and what we would like to know. In fact, that gap is so large that it's the largest gap I know of that's ever been called understanding. I'm going to try to convey to you today what we know about complex systems, and in particular, what we know about complex systems from the perspective of emergence, which I know is a big topic in your joint center. So I'm going to try to strip away some of the mysteries and misconceptions about emergence, and then give you some of the examples of it that are from our own work, some of which is in collaboration with people who are involved in your center. So here's what I'm going to propose to discuss in the next hour. I want to, first of all, talk a little bit about emergence and complex systems. Okay, there we go. Start my timer. I want to talk about emergence and complex systems and describe how they are related. And then I want to point out to you something that I think is very often missed in discussions about emergence, and that is the idea of emergent rigidity. And that, I think, is very important, and you'll see why when I discuss it. And then I want to give you some examples. I'll start off with some to do with magnetism. I'll talk a little bit about superfluids. I'll talk about turbulence, both its onset and fully developed turbulence. I'll talk a little bit about some recent work that we've been doing on the charge order in high-temperature superconductors, and I'll talk finally about stochastic Turing patterns in biofilms. In fact, that last topic, I'm just going to show you a little bit about that. That's work done in collaboration with Ron Weiss at MIT and his group. And then at the end, I'm going to point out that one can exploit emergence and the properties of emergent phenomena in order to model nature, and I'll give you an example of that, which is the modeling of a very complex geophysical ecosystem, where one can make predictions which one would not think one could do simply because of the complexity of the system. All right, so let's talk about what complex systems are. It's very hard to define complexity, but at least we can say something about what complex systems are like. So complex systems, from my perspective, are systems which have strong fluctuations, but they also have unpredictable and nonlinear dynamics. So because they are strongly fluctuating, that makes them very difficult to describe by most of the tools of physics. They're unpredictable and have nonlinear dynamics, so that means they may exhibit chaos or worse things than that, such as turbulence. They usually involve multiple scales of space and time, and all those scales need to be integrated together and produce an emergent structure at usually the largest scales, and those are the phenomena that we're interested in, for example, in materials science or in say, cellular biology or synthetic biology. Complex systems are also different from physical systems. In my perspective, real physical systems are never complex. They're just complicated. But complex systems have all of those things and more. They have active components. So when you try to hit them, they fight back. They do things that you didn't expect. They can adapt. They can evolve. So they have activity. And they also have layers of feedback loops that are nested and which are contributing to multiple hierarchical layers of systems dynamics. So these are incredibly difficult systems to deal with for all of these reasons, and that's why they are, in fact, the hardest and most exciting problems to work on at the moment. And why is that? Well, just think about the natural development of the sciences. As science starts, it started maybe the modern era of science started maybe 400 years ago. You start off with simple things like, say, a trajectory of a projectile or the moon or something like this. You want to pick the low-hanging fruit first, and for those systems where you can solve them, the reductionist approach is valid. Virtually everything we teach our students in classes is stuff that is hundreds of years old, at least conceptually, and the reductionist approach works, and we can proceed to teach that way. But ultimately, you're going to lead problems. Ultimately, you're going to encounter problems where the strong interactions are going to be important, and you're going to start running into emergent phenomena and then complexity. So this is why this topic of emergence is really so interesting to the general public and to scientists at large in many different fields because it involves the common threads of complexity. Now, where does the understanding of emergence come from? I would say that the opening salvo was fired by Phil Anderson in a very highly cited and influential opinion piece in Science in 1972. And this was called "More is Different." And this is a phrase that people talk about all the time. And what he was trying to say was this: as you make systems bigger, as they involve more and more degrees of freedom, which interact with each other in complex ways, the actual nature of the behavior can change. It can change through broken symmetries, which I'm going to talk about, and it leads to a hierarchical structure of the way that the physical system is organized. And in fact, here he goes even further and talks about the hierarchical structure of science. So this was his idea that reductionism breaks down when you start dealing with systems which have more than a single or a couple of particles, and we'll see that that's true. So I want to do an experiment now to teach you very quickly the most important thing that you need to know about emergence. So I'm going to do this experiment first, and then I'm going to make you do an experiment as well, and then there's going to be a quiz question. For those of you who are watching remotely, I hope you can see what I'm about to do. So this thing here is called a chair, and I'm going to exert a force on it, and there it goes. Okay? I can push it, I can send it halfway across the room, and it can crash into something. I managed to transmit a force. And just in case you missed it the first time, let me do it a second time. Okay? So, okay, now that's a really interesting, very surprising experiment. It shouldn't do this. Now, why do we think it's surprising? Okay, let's do an experiment. Let's see if we can make the roof move in this lecture room. Okay, so everybody, get your finger. I'm serious. Everybody get your finger. Okay, and now poke upwards, just like I did with my chair. Right. Okay, anybody see the roof move? Even some people here have the ability to measure some distances on the scale of atoms. Anybody see the roof move? No, it didn't work. Okay, now, why is it different? Why is doing this not moving the roof, or even moving anything, and doing this moves the chair? And you might say, well, you know, the chair's solid and stuff like this. But we all know physics. We all know basic, graduate level, undergraduate level physics. And we all know that if I asked you, quick, write down the Hamiltonian that describes the motion of the gas particles in this room and the motion of the particles, the atoms that are in the chair, that Hamiltonian would be exactly the same. It would have kinetic energy, and it would have potential energy. And because it has kinetic energy and plus potential energy, when I try to work out how the system behaves, I would look at that and I'd say, well, it's the same Hamiltonian, they should do the same things. And yet, I push a fluid, I push the gas, and it does not transmit a force. I push this thing, and it does transmit a force. Same mathematical description, but they do completely different things. So what I've just shown you then, and what you've seen for yourself, is that if I talk about a bunch of particles bouncing around in a box, they're in the fluid state. That's a fluid, okay? Then I go to low temperatures. I form a solid. In this case, I said it's a crystalline solid. The characteristics of that crystalline solid are very different from the fluid state. You have a periodic crystal lattice, for one thing. That's the thing that people usually talk about. If I ask in my class, emergent states of matter, quick, tell me what is the characteristics of a solid, everybody will say, yes, it has periodic atoms, it has Bragg peaks. Okay, some of the people here who have been in my class, they know that that's true. But of course, that's not true. You can have things that are solid that are not crystalline, and they're certainly not defined by Bragg peaks. In fact, the thing that really defines them is that they have static shear rigidity. They can transmit a shear. They experience a restoring force when you try to shear the material. So there's some certain response characteristics of a solid that are different from a fluid. Now, why is this interesting? Okay. It's interesting for the following reason. The underlying physics of the crystal is exactly the same as the fluid. Total energy is kinetic energy plus potential energy. If I know the Hamiltonian, I know all the dynamics according to classical mechanics, and yet they have the same thing, but they behave differently. So lowering the temperature didn't change the interactions between the atoms, but it did change the outcome of those interactions. And so that's why this is interesting. So what's the conclusion from this very simple experiment? The pairwise interactions between the atoms didn't change. The correlations, though, between them changed when the temperature was lowered. It's as if the atoms decided to get involved in a conspiracy. Okay? They all decided we're going to conspire to be exactly the same distance apart from all the other atoms. And however much you move the other atoms, I'm going to make sure that I'm the same distance from the atoms around me. And all the atoms agreed to partake in that conspiracy, and so the correlations between the atoms changed when the temperature was lowered. And so the solid state emerged as if by magic out of the fluid state. That's the thing that's so surprising, that the solid state emerged out of the fluid state even though nothing had changed between the individual degrees of freedom. So in some sense then, we can say that the new state that we formed by lowering the temperature has its own new laws of physics. So let's have a look at them. So here they are. When the atoms form a lattice, then it seems as if they are connected by springs. The material that you get has elastic response. It is solid. And the response of the solid to external disturbances is completely different from that of a fluid. So the new long-range forces have emerged. These are elastic forces. They're completely different from the original forces between the atoms. The original forces between the atoms might be some hardcore repulsions, maybe some long-range Leonard-Jones or dipole interactions, whatever. But now my description of a solid is a bunch of balls connected by springs. If you go and look at an elementary solid-state physics book, say Ashcroft and Mermin or something like that, when you start off with a chapter on crystals, you write down the Hamiltonian for a crystal. It's a bunch of particles joined together by springs, and then you work out the quantum theory of that, you get the theory of phonons, and so on and so forth. But the starting point for your description of a solid or a crystal, and your starting point for the description of a fluid should be exactly the same. But in the books, we don't do that. Why? Because we assumed that once it's formed this solid emergent state, then we start off with that. And these springs are in some sense emergent. They are the thing that emerged when we went from here to here. Now, what is the origin of the new behavior? You know that once you have the description of a system like this, it has modes of vibration of the individual atoms. They are coupled together. You can get sound waves sloshing backwards and forwards. There's all sorts of interesting modes that the system can exhibit, which are different from what it has in a fluid. A fluid has a longitudinal sound wave. A solid can have transverse sound waves. So it has different excitation spectrum. So all of those new laws are collective and it comes from the statistical behavior of the atoms. And we know it comes from the statistical behavior because all we did to go from here to here was to lower the temperature. We didn't change anything else. And the temperature tells you about the thermal properties of the material. So this transition happened not because you just stuck things together in like Lego bricks to make an architecture that is rigid, but thermodynamically, this is what happened. If you take a piece of gel or rubber, something plastic, it is a solid, but it's a solid made up out of polymers that are cross-linked together. Each of the polymers on its own is floppy, and if you took a polymer and tried to see if it is solid, it absolutely is not. But you cross-link them together, you allow them to not pass through each other, to have interactions with a solvent, and the collective behavior of all of that system of polymers cross-linked together in solution ends up being a gel or a rubber, something that is solid. So these are collective and statistical laws. So is it really true that when we can say the solid state has its own new laws of physics? Well, yes, it really is. Because let's suppose you just look at the level of description of the solid, then you can't really tell what were the original interactions between the atoms. All you can see is the elastic behavior of the solid itself. In fact, this is why it took us so long to discover that atoms even exist. because I don't even need to know anything about atoms or whether they exist, and certainly what their force laws are, in order to be able to explain the elastic behavior of solid materials. So at the level of description of a solid, where you just don't look any further, you just look at the thing you've got in front of you, what's at the lower levels of description, higher energies, smaller length and time scales, those things don't really appear here. This thing can all be described by a bunch of balls connected by springs. I have a spring constant. That's it. If I have an elastic material, I might have a tensor description of the elastic properties, but none of that really, I need to know anything about the microscopic force laws. Now, if I know about the microscopic force laws, I can then try to compute the effective behavior at this scale, but that's not an easy thing to do. It's better not to try. Better just to say we have some elastic constants and move on. So the fact is that because we have emergence, because at the level of description we can describe the interactions in a very simple way, emergence means that we can do physics at one level of description without having to worry about what happens at a lower level of description. So what I've just said is what's on this slide here, it took so long for the existence of atoms to be deduced because we can't really see how, once you just look at the large-scale behavior, you look at the material itself and look at its elastic behavior, it's hard to see how that is related to what happens at the microscopic level. So what that really means is this. When we do atomic physics, when we do chemistry, we don't need to worry about the lower levels of description. How many people here do some kind of chemistry? Some of you do. Okay, great. When was, Tahir, you did. When was the last time you had to worry about the radiative corrections to the mass of the top quark? Never, right. You never had to. But why? Right? I mean, shouldn't you be writing down the Hamiltonian for matter, which involves the standard model, the weak interactions, the strong interactions, and all of that? No, you don't need to worry about that. It's all absorbed into the mass of the proton, or the mass of the hydrogen atom, something like this. So the fact that you have emergent properties of atoms allows you to then do chemistry. You can say, I don't need to worry about those things. All of those things have emerged into a few phenomenological parameters, and then I don't need to worry about all the other 23 adjustable parameters in the standard model of particle physics. Okay, so what I've told you so far is that emergent levels of description absorb the properties of lower levels of description into phenomenological parameters. And the good news is there's only a small number of those. So in fact, I have this joke that I sometimes have with my high-energy physics friends. So they say, well, what we do is very fundamental, and you just do condensed matter physics, or even worse, biological physics. So our stuff is much more fundamental. So I say, well, that may be true, but when I write a paper, the prediction usually has no adjustable parameters, or maybe one adjustable parameter. But when you write a paper, it has 23 adjustable parameters. Okay, which one do you think is more fundamental? Okay, so they don't like that argument. Okay, so now why is fundamental physics hard? So there's two ways you can go. One is when I do, and you do material science or condensed matter physics or biological physics, you're starting at some level of description. You're a chemist, so you're saying the world is made of atoms. I know it's really made of other stuff down all the way down, but never mind, it's made of atoms, and then I want to know what happens when I take these atoms and put them together. Okay, so that's going up in length scale. Okay, going down to the fundamental physics, as it were, one has to go against the flow of emergence. As you go from a description like this down to the more fundamental description in terms of the actual interactions between the atoms, then that's not unique. And because it's not unique, you don't really know what the microscopic physics is. So reductionism is essentially doomed, but there's a limit to how low you can go, but the collective properties of matter should be understood and can be understood without requiring knowledge all the way down. And that's the great miracle that enables us to be able to do science in the first place. Because there are some sciences that this doesn't work in. It won't work in, for example, economics. Okay? Why is economics a dismal science? Well, it's not because people haven't been smart enough or whatever. It's just it's a strongly coupled fluctuating system, and we don't know if there is separation of time and length scales and so on. We don't know how to do this magical trick of coarse graining and looking at different levels of description in such topics like, say, economics or finance or whatever. So it's not always true that you can do this. It's amazing that we can, and because we can, the physical sciences are very successful, but it absolutely isn't mandatory. All right. Now, along the way, though, we have to be careful to only ask the right questions. Not every question can be answered by this kind of level of description, this kind of material, this kind of thing here. So I will come back to that a little bit later. Okay, now the other thing I want to tell you about is the characteristics of emergence. I'm going to define emergence for you in a few minutes, but I want to just make this other point. Emergence is associated with loss of uniqueness. So think about this. We talked about the fluid turning into a solid, into a crystal. The fluid state is still possible at low temperature. When you do the statistical mechanics, that is a perfectly allowed solution of the statistical mechanics. It's just much, much less likely, and in fact unstable, than the solid state. So what's happened is as you lower the temperature, the system can now be in not one state, but several states. So there's a lack of uniqueness. When you have emergence, the system can choose between different possible states. So even though you've got a deterministic set of equations, the outcome of those equations does not have to be unique. Even a deterministic equation can have multiple solutions at the same values of the parameters. So it's associated with loss of uniqueness. Now, if you have different states in the system, then they are separated by what we call a phase transition. So I will talk about an example in a few minutes. We'll talk about, say, a magnet, which can be at high temperatures. The spins, the electron dipole moments can fluctuate up and down or in any direction in space, and so there's no net magnetization. But when you cool it below the Curie temperature, the material acquires a magnetic moment, a magnetization. And so phase transitions separate the states, say, between a paramagnet and a ferromagnetic state of a material, and we'll talk about those phase transitions as well, because they are a characteristic of emergence. Whenever you see emergence, there is a phase transition associated with it, which is collective and is described by the fluctuations. Okay, so new collective properties arise in emergent states. And once you have this idea, then you start to think, okay, well, crystals, that's a good example. Magnets, that's pretty obvious. Superconductors, well, superconductors, quantum Hall effects, some of the exotic quantum states that are studied here at this university. These are all emergent states. They all have the same ions and electrons that are in the material, but they behave in different ways because you're changing the interactions in controlled ways. And then I'm going to talk about a little bit about turbulence, but then you can say, well, maybe everything's emergent. Maybe gravity is emergent. Maybe life is. Do emergent phenomena bring molecules to life? Those are really important questions. So let's talk about those. So when we think about emergence and complexity, what we normally think about is this kind of continuum. So I'm a condensed matter physicist. Some of the people here are chemists, so they are sort of perhaps more interested in atomic physics. But these are the sort of lowest levels of description. And then as you start to go to more complicated systems, like the things that you're interested in, cell biology, biofilms, multicellularity, ecosystems, community structure, social systems, even economical systems, you might say, well, these systems these are emergent properties, starting from the level here at atomic physics, all the way to these larger systems, more complicated systems. That's the signature of emergence, and that's absolutely true. And at some point along here, complexity starts. Condensed matter physics, you have many emergent phenomena, like superconductors, quantum Hall states, and so on, but they're not very complex. They may be complicated. Complexity really starts when the bio word gets into it, in my opinion. So, but anyway, emergence begins with strongly interacting condensed matter. And I think most people would agree with it, but it's not actually true. Okay? Because let's start off at this level of description, the atomic physics one, which was our starting point. Well, let's think about where atoms come from. Well, there's condensed matter physics and cell biology and so on over here. Now atomic physics is over to the right, and underneath atomic physics we have nuclear physics, we have quarks and gluons and whatever down there, strings or whatever it might be. Okay? These states of matter also exhibit emergence. There's emergent states of quarks and gluons. One of the emergent properties of quarks and gluons is the proton and the neutron. These are bound states, like the solid state, if you will, of quarks and gluons. If you go and spend $800 million, you can build a relativistic heavy ion collider at Brookhaven. You can smash heavy nuclei together, and you can see what happens when you take the quark-gluon plasma and raise it to high temperatures. You unbind things, and you can see properties of matter at higher temperatures, but this is all this kind of matter here. So there's emergence at every level of description, and even strings are thought to be emergent. We know that because, why? Because if you have a real theory of strings, of the ultimate structure of the universe, you would say there's one ground state. Well, we know from work that Joe Borczynski and other people did, the number of states is 10 to the 500. So you have a crisis. Even strings are emergent. They have this multiplicity of states, this non-uniqueness. And so we know that maybe the most fundamental interactions are emergent as well. So emergence really has to be a real part of not just the physicist's toolkit, but everybody's. Now, I want to talk about some misconceptions about emergence, because there are many. And the one that I see most frequently stated is this. Probably if I asked everybody coming into the room, before you sit down, write down on a piece of paper what you think emergence is, and then we'll compare answers at the end. I'm pretty sure that most of you would say, or many of you would say, emergence is something that is surprising and unpredictable, that just comes out of a system and can't be understood. Am I right, Rashid? Right. Dean Bashir at the back there is nodding in agreement. That is what people normally think. And here's from Wikipedia, paraphrasing Dow in 1987, the idea that weak emergence describes new properties arising in systems as a result of interactions at an elementary level. That's all well and good. It is stipulated that the properties can be determined only by observing or stimulating the system and not by any process of analysis. Well, my students in emergent states of matter solve dozens of homework problems using analysis throughout the semester, and they predict all these things. So there's many statistical mechanics techniques to predict emergence in physical and biological systems. The subjective difficulty of a calculation should not be part of the definition. Okay, so what is emergence then? So I think emergence, it's safe to say, is a non-mandatory property of the entire system due to the interaction and self-organization of its components. And again, I say non-mandatory because it's associated with a loss of uniqueness in large-scale properties as some parameter is varied. For example, the temperature, or maybe the strength of interactions between things. And I give the example here of a magnet. Now, the important thing about emergent states is that they exhibit generalized rigidity. We talked about the rigidity of that chair. Right? We did that little experiment together. That's an outcome of the collective interaction between the components, the thing that I call a conspiracy. Okay? When you have systems as complicated as, say, a superconductor or a superfluid or something, the rigidity is not just pushing something, it's something more complicated. It's a rigidity associated with the wave function that describes the system, for example. And so that's why I call that a generalized rigidity rather than just the classical continuum mechanics rigidity. Now, some of the universal outcomes of emergence are important. I'm just going to quickly mention them before we get into some examples. So emergence is associated with a breaking of symmetry. Okay? So in a magnet at high temperatures, the spins can point in any direction. So that means that you have a system which has full rotational symmetry. But at low temperatures, they align along some randomly chosen direction, say the Earth's magnetic field, and so the rotational symmetry is broken. Most of the emergent properties that I can think of arise from a breaking of symmetry. Now, what that symmetry might be hard to identify. What is that symmetry when you talk about, say, the emergence of life? Don't know. Okay. So, but this is really systems where we understand the physics of it. This is how they're described. Emergent states of order can have localized holes in the order. So you can have a crystal. But crystals aren't perfect. Crystals have many kinds of disorder in them. You could have an atom that is not at its correct site, so you could have a vacancy. Much more importantly, you can have a dislocation. I think most people here know what a dislocation is. And those dislocations can have a topological charge. For the material science community, in a dislocation, that would be called a Burgers vector. In a superfluid, the topological charge is associated with the vorticity of a quantum vortex line. So these are important, these topological defects that have some topological aspect associated to them. And I'll give you an example, two examples of that in a minute. And then lastly, the low energy excited states or emergent states of matter have generic behavior. So what I mean by that is, in the same way that you can say that all materials, when they form a solid, should exhibit continuum mechanics. And I can write down the laws of continuum mechanics without knowing anything about the existence of atoms. People like Cauchy and so on did that 200 years ago. They were able to do that not knowing anything about the microscopic world. Okay? So that is because the small excitations of the system are universal, and that universality can be exploited to make predictions. So here's one of these examples that I want to start with. So this is the Nobel Prize for Physics in 2016, given in the field of condensed matter physics. And this is to three English physicists who came to the United States courtesy of Margaret Thatcher. And this is the British gift to American science. And I want to talk about the work that David Fowlis and Mike Kosterlitz did very, very briefly. So they worked on superfluids. Now, what is a superfluid? Well, you know what a normal fluid is, such as honey. It's a normal fluid and it flows. In this particular case, it's a very viscous fluid. Okay, it flows in a very viscous, slow way at room temperature. But if you take superfluid helium at say 1 degree above absolute zero, it's superfluid, and that means it basically functions as if it had no viscosity. That's what we mean by a superfluid. Now, it actually does have viscosity. How it actually is correctly defined is something I'm not going to get into. But for the moment, think of a superfluid as something that flows without viscosity. So if you make the fluid go round in a circle, it will just keep on going forever. It's perpetual motion due to quantum mechanics. Now, the way that Kosterlitz and Fowlis described this, you might think they'd say, well, okay, we have to start worrying about the forces between the helium atoms and the substrate and all of that stuff. They didn't. Their model that they looked at was simply a model of this. Take some arrows, lay them down on a plane, let those arrows interact with each other in some way that just depends on the orientation between them. That's it. Write down the simplest theory that you can, and they were able to predict a whole bunch of interesting properties, some of which I will just show you right here. What they predicted was that system will spontaneously order and have its own shear rigidity. Now, the ordering in a superfluid is a quantum mechanical ordering, but what it essentially means is that the quantum wave function orders in a particular way, and what that means is that it has a rigidity, meaning you can propagate waves, certain types of waves, through the helium. And this prediction was verified. So here you have the superfluid density. That's essentially the strength, the elastic strength of the fluctuations in the wave function in the superfluid. And in fact, these here are measurements that were done here at UIUC. And this graph is showing you that elastic modulus as a function of the critical temperature of the superfluid, and that's in complete agreement with the theory. So the thing about this is that superfluids in 2 dimensions are pretty complicated, but Kosterlitz and Fowlis' Nobel Prize work predicted how this emergent rigidity of a superfluid in 2 dimensions came about just from looking at the simplest way that you can lay down arrows on a plane. It's fantastic. So the moral of the story is this: very simple models can predict very complex phenomena, because when you have the complexity of what's happening underneath disappears, and then you can make a simple model that describes the phenomena that you're interested in. So in other words, if there's many different microscopic models that describe superfluid helium, one that includes all the interactions between all the helium atoms and the substrate, very complicated thing. The sort of thing that David Sepperly can put into a computer and predict very precisely. Or you can say okay, since everything is universal, let's look at the symmetries of the problem, and then let's look at arrows pointing on a plane, and let's work out the theory for that. Again, how to do it in detail, you'd have to take a graduate course, but you can do it. And that theory also produces exactly the same results as the more microscopic theory. The microscopic theory can tell you what the temperature is you have to go below in order to see superfluidity. The theory that you produce by just laying down arrows on the plane can't tell you that. So as I told you, this approach can't answer every question. But if you say, I don't care what the critical temperature is, where superfluidity starts, all I care about is how the elastic modulus varies with that critical temperature, then you're in business. So some questions you can ask, some you can't. Okay, so now let's talk about the onset of emergence. I'm going to now go very quickly through a bunch of examples. And I'm going to go quickly through them just to show you what you can do with these sorts of levels of understanding. Not that you're going to, I expect everybody to sort of understand all the details, but I just want to give you, put some flesh on these bones. If you want to ask me questions about any of them afterwards, please do. So I want to talk about the critical behavior in a fluid. So I told you that emergence is usually associated with a phase transition. So this is the pressure temperature phase diagram of a fluid, and as you can see here is a line of coexistence between the gas phase and the liquid phase, and then between the liquid phase and the solid phase. And when you have a liquid and a gas in coexistence, you get a meniscus between them. As you go towards the critical point, that meniscus disappears. Why? Because I can go continually from gas to liquid by going around like this in the phase diagram without ever encountering a critical point. Okay. Now, what happens near that critical point is like this. So these pictures show you the density in the fluid near its critical point. A liquid is more dense than a gas. So think of the black squares as being liquid and the white squares as being low density, being gas. As you get closer and closer to the critical point, you see that the size of the domains grows and more of the material becomes black. Now, what I'm not showing you on these graphs, but you might be able to see them for yourself, is that if I took, say, this picture here exactly at TC, if I, say, look at that and then took this part here and photographically enlarged it, it would look the same. The system looks the same on all scales. This system definitely does not look the same on all scales because the size of the blobs, the black blobs, is always the same size. But here you have blobs which are big, blobs which are medium-sized, blobs which are slightly smaller, blobs which are smaller all the way down to just one single pixel. So this at the critical point is scale invariant. That scale invariance is a crucial part of the onset of emergence. So here is the phase diagram in a magnet. What I'm plotting here is the magnetic moment of, say, a piece of iron as a function of temperature. As you cool it down, it has no magnetization. Once you go below this temperature here, then it starts to become magnetic in some direction. And as you lower the temperature further, the magnetization gets stronger and stronger. And that's described by this formula here. The magnetization goes as the absolute value of T minus the critical temperature raised to some exponent, beta. If you were in my class, I would ask you to produce an instant theory for what the exponent beta is, and I would lead you through that. And most of you would be able to do that exercise, and you would predict that this exponent should be 1/2. But it's not. It's about 0.3265, some other number like that. Some weird number that renormalization group theory explains and predicts. So this is one thing that happens. Another thing that happens is this. Let's suppose I take a magnet, but it's not magnetic. Okay? It's at a higher temperature than the temperature at which it spontaneously becomes a magnet. I then apply an external magnetic field. The spins orient with the magnetic field, and so it will start to have a magnetic moment. How much? Well, Curie solved that problem. Curie's law says that the bigger the field I apply from outside, the more magnetization it will induce on the inside. So if I take a material that has the potential to be magnetic, apply an external magnetic field, the induced magnetization in the material is proportional to the field. That's called linear response theory. That's just common sense. But it breaks down at the critical point. At the critical point, I sit at the critical temperature and measure how the magnetization is related to the external field, H, that's what I'm plotting over here. The answer is it goes like 1 over delta, where delta is a number that you might guess to be 3, but in fact is a number like 4.2163 or something like this. So the linear response theory breaks down. These two facts can be combined into a single scaling formula that says that magnetization is ostensibly a function of two variables, temperature and magnetic field, but in fact is just a combination of H and T as shown over here, a simpler formula. And what that means empirically is that if I take all magnets, I plot their magnetization in the scaled way versus the scale temperature. Here are shown 5 different magnetic materials, and all the data fall onto one same curve. You can't tell the difference between any of those magnets when plotted in this way. The magnetization emerges in a universal way. And the solid line going through here is the theoretical prediction from the normalization group theory. So it works fantastically well. This is called data collapse, and it's one of the signatures of emergent order at the onset of emergence. Okay, now I want to talk about something completely different. I would like to talk about turbulence. So here's a sketch of turbulence from Leonardo da Vinci. And most of you are saying, well, I don't know anything about turbulence. And that's okay, because pretty much nobody else does either. But I can show you some interesting things that we can learn about turbulence, not from being able to solve the underlying equations of motion, but just from being able to apply some of the ideas from emergence and universality. So let's talk about the onset of turbulence. So this here is a pipe. The pipe has radius r. It has fluid going through it with some average velocity v. And the fluid provides drag on the walls of the pipe, which we'll call tau. And the control parameter in this experiment is called the Reynolds number. So it's the product of the velocity, the radius or the diameter of the pipe, and the viscosity. The fluid has a viscosity. We divide the viscosity by the density. That's called the kinematic viscosity, and that's the number that comes in here. This is a pure number. If it's small, why would it be small? That would be because the viscosity is large. So small Reynolds number is like the honey that I showed you a few minutes ago. On the other hand, if the viscosity is very small, like in the superfluid, then the Reynolds number would be very large. And that flow, if you took a fluid that has no viscosity and you just put your fingers in and swished it around, it would very quickly end up looking like Leonardo da Vinci's picture. So that's turbulence. Okay, so turbulence was first investigated scientifically by this gentleman here, who may or may not be this person shown in the sketch. This is Reynolds' original experiments on pipes, and he was the one who defined the Reynolds number for the first time. And what he found was if I put a little bit of ink in the inlet here, and let the fluid flow through the pipe, the ink will stretch out and make just a straight line like this. And that flow is smooth, it's predictable, and it's called laminar. Then he did the same thing, but he put the fluid in at a much higher speed. Then the fluid was flowing through the pipe at a higher speed, and once it's really got going in the pipe, you can see that the ink starts to make these swirly, twirly patterns, kind of like Leonardo da Vinci's picture. And that's what we call turbulent. It's irregular. It is difficult to predict. But in between, it transitions. This is how it emerges, how turbulence emerges. It emerges in flashes, or nowadays we call them puffs. Laminar, turbulent, and so on and so forth. People have been trying to understand this problem since 1883. Now we have a pretty good understanding of it. Now we know, for example, this. If you measure how much of the pipe is turbulent, so if you look at this pipe here, if you start apart from this bit at the beginning, all the way down here, the fluid would be turbulent. But in this pipe, none of it is turbulent, and in this pipe, this bit is turbulent, this bit isn't, this bit is turbulent, this bit isn't, so there's only a fraction of it that is turbulent. If you try to figure out what fraction of the pipe is turbulent, That's the turbulent fraction here. As a function of the Reynolds number, what you find is that at low Reynolds number, it is smooth like this. At high Reynolds number, it is all essentially turbulent. And in the middle, it's like this, but the way it goes from nothing to something follows a power law, as you can see in this log-log plot, and that power law is described and predicted by statistical mechanical theory that I worked on with Hongyan Shi, who's sitting here in the audience, and other people in this field. So this measurement that I just showed you is not actually a pipe. It's actually a circular pipe. It's a very thin, 2 cylinders, very with a very narrow spacing between them. The outer one is rotating. The system is very small, so that the length along here, going all the way around, is much greater than the spacing between the cylinders and the height. And so this thing is essentially a pipe, but it's a pipe with periodic boundary conditions. It's a pipe that goes round forever. And the turbulence is little black streaks that you see here. So what you do is you look at this point here, the fluid rotates around you. You see nothing, and then black, which is turbulent, then laminar, then turbulent, laminar, laminar, turbulent, and so on. You take these pictures for first rotation, second rotation, third rotation, fourth rotation. You stack them up one underneath each other, and what you end up producing is this pattern here. And this pattern here, you can see that if this is time, because we're talking about the time development, this is the space, this is going all the way around this circular pipe. The blue is the turbulence, the yellow is the laminar. You can see that at long times, this situation is at long times laminar. That's because the pipe is not turbulent enough. The outer cylinder is rotating too slowly. When this outer cylinder rotates rapidly, you get lots of turbulence, and at long times, you always see turbulence. And then sometime in the middle, you may see a little bit of turbulence, but not everything is turbulent. And these things, so the pictures I showed you came from this experiment, not really from the pipe experiment. But it's basically the same principle that applies. Now, if you go then to turbulence that is very, very turbulent, you can ask, can we understand that? Is that emergent too? And surprisingly, it does show some properties of emergent. It's not complex, but it's complicated. So here's the picture then. This is the Reynolds number that I showed you before. The experiments I showed you, at least in the pipe, are around Reynolds number 2000. If you go to Reynolds number about 1 million, or something like this, then you see all sorts of other phenomena to do with turbulence, kind of like the ones that Leonardo da Vinci sketched. Now, I just talked just now about the transition to turbulence, but now I want to just say a few words about this one. So what you do is you take your pipe. Remember I told you can have a little roughness in it? Well, this experiment was done not recently. It was done in 1933. And what you do is you put little sand grains, carefully monodisperse, glued to the side of the pipe. You measure the pressure drop per unit length divided by rho u squared, and then you measure the friction exerted by the turbulence on the pipe. Now you know that when you walk, the air drag is proportional to how fast you move. If you ride a car, once you go above a certain speed, the air drag goes not proportional to the speed, but to the speed squared. And that's why you get that's a signature of turbulence. In fact, that corresponds to why it costs so much energy to drive fast. So if you want to limit the use of oil and petrol in a country like the United States during the 1970s, when there was an oil crisis, there was a ban on driving over 55 miles an hour. Why? Because going from 55 miles an hour to 70 miles an hour, you use twice as much fuel, even though the difference between 55 and 70 miles an hour is not a factor of 2. That's because the friction scales with the velocity squared when you have turbulence. Okay, so when you investigate this scientifically, what you find is that beyond the transition to turbulence, which is somewhere around here, the friction this is divided by Reynolds velocity squared, so it follows this law here, where it goes as Reynolds to the minus a quarter, and then eventually at large Reynolds numbers becomes independent of Reynolds number. That means the friction is going like the velocity squared. But then the friction depends on how rough the pipe is. And if you take those data that I just showed you here, this sequence of curves, smooth pipes, rough pipes, this is the friction measured for all these different pipes, what you find is that if you collapse the data using ideas of emergence and universality, the data collapses like I've shown you here. If you actually improve that to take into account the strong fluctuations, what you find is that the data all collapse onto one universal curve. And why is this a big deal? This is absolutely fantastic, and it's fantastic for the following reason. Just by measuring the pressure drop across a pipe, this experimentalist, Nikuradse, actually was able to measure for the first time the strong fluctuations that you get in turbulence. Nobody had ever done that before. In fact, this wasn't understood until we interpreted this experiment 80 years after it was done. It could have been done by anybody after 1933, but we did it. Why? Because we knew about emergence, we knew about universality, we knew about phase transitions, and so on. Okay, so I want to just talk for a few more minutes about a couple of other topics very quickly. So this is one, I want to talk about emergent rigidity far from equilibrium. I told you that rigidity is the important thing in thinking about emergence. So I want to talk about emergence in electronic systems. So let's suppose that what we're going to talk about is a high temperature superconductor. Okay, in this case, lanthanum barium copper oxide. You would say, and you were taught this in elementary solid state physics, that you have some electrons, you have some ions. Your natural presumption would be that the electrons would be uniformly smeared out throughout the system. Okay? But it's not true. Okay? It doesn't have to be like that. The system can spontaneously order, and the system can have a pattern that emerges. The electrons can self-organize to form a pattern. And the pattern they self-organize into is a pattern like this. Think of the white regions as being electrons having a higher density, and the black regions as electrons at lower density. This describes charge order, periodic charge order in a high-temperature superconductor. So what's happened is that the electron interactions have spontaneously broken the translational invariance. You would think that the system would be smooth and uniformly distributed in terms of the charge density, but that doesn't have to happen. Now, this picture here is a movie. And this is the movie that describes an experiment that we did with Peter Abamonte in the physics department and members of his group and my group. And the thing that you can see here in this movie, it might even replay. Let me make it, there it goes. It'll play again. Just the threat of me going over there made it restart. You can see that this is not a periodic pattern of stripes, but it has dislocations in it. Those dislocations are topological defects. And this movie evolves slowly because of the motion of those topological defects. So the topological defects that arise due to the emergent electronic charge order determine the macroscopic properties, and in fact may contribute to the high temperature superconductivity, because the lengths, the energy scales of these fluctuations that we were able to measure using ultrafast X-ray scattering actually predicts to a good approximation what the critical temperature is of this superconductor. Our understanding and our theory of this requires nothing about understanding the mechanism of the superconductivity. We just need to look at the emergent charge order. Now, I want to end these examples with one that we did with Ron Weiss at MIT, and this is a paper that was published earlier this year, David Carragher et al. This is the idea of a stochastic Turing pattern. So let me tell you what a Turing pattern is. And let me tell you what a Turing pattern is, I want you to think about something completely different now from what we've talked about. I want to talk about an ecosystem of predator and prey. Okay, so a predator might be, say, a wolf. Prey might be, say, a sheep or something like this. Okay, so the red are the wolves. Now, what I want you to imagine is this. that when there's a lot of sheep around, what are the wolves going to do? They're going to come out of the forest and flock to where the sheep are because there's plentiful food there. So what's going to happen then is that the prey will make little baby prey, and that will so now there's more of the sheep around. So what's going to happen is that because there's plenty of sheep, of the prey, then what's going to happen is the predators are going to come out and will start trying to eat the plentiful supply of food that they have available. Now, what's happened in this particular situation is I want you to imagine that the predator, the wolves, can run around much faster than the prey, the sheep. So what's going to happen is that the wolves can basically move very quickly around the prey, stopping them escaping, and then they're going to start eating them. And so what you're going to end up with is you're going to get clusters of prey, the sheep, surrounded by wolves. So you'll get patches, and those patches are some kind of pattern. Now, the predators don't keep producing forever, because if they did, then they would go extinct. The predators compete amongst themselves. The wolves say, hey, leave that sheep alone, that's for me, and so on. Okay? When they do that, when you have competition between them, then the predators are also fighting amongst themselves, and that then causes the system to come into balance. There's a balance between the predators and the prey, and so the system doesn't go extinct. But if you look at the system, it's going to have patches of predator and prey around it. Now, whether those patches are going to be spots or stripes, that's something for the theorists to predict, but that's the basic idea, and that's called a Turing mechanism. If you go and work out the theory of that, as Turing first did in the 1950s, in a completely different context, this axis here is the ratio of how fast the predator can diffuse or move around compared to how fast the prey can diffuse or move around. So this is the ratio of the mobilities. And this here is just how strong the predation is, how quickly aggressively they eat, and so on. So if you look at this picture here on the right, this is what Turing himself worked out, that basically if I have a certain predation rate, and I ask, when would I start to get patches, or when would I just start to get some uniform system? The answer is, I would get patches only when the diffusion coefficient ratio was, in this case, say 60 or 80 or some large number like that. So the theory predicts that if I had such a system, if it was literally predator and prey, if the predators can move very much faster than the prey in the way I described, you would actually end up with patches of prey surrounded by predators. But otherwise, the system would just be uniformly dispersed. You would have no pattern whatsoever. But the number of degrees of freedom in the system is small. The number of predators is not infinity. The number of prey is not infinity. They may be 100 or something like that. So there can be large fluctuations. And when you work out those fluctuations, what you discover is that you can have random patterns created just by the number fluctuations in the system. Just by the fact that sometimes a predator will make a baby predator, sometimes it won't. Sometimes a prey will die, sometimes it won't. Sometimes a prey will make 2 or 3 babies, sometimes it won't. Those fluctuations in the number, demographic noise, turn out to allow you to have patterns even when the ratio of the diffusivities, the mobilities, is not as high as is needed in regular Turing patterns. So noise, in this particular case, increases the range where you get emergent patterns. Now, what Ron's group did was a very beautiful experiment. They looked at signaling molecules in a biofilm. And they looked at those signaling molecules. They created a complicated circuit here, which basically is an activator and inhibitor. And they engineered it in such a way that you could see the concentration of the signaling molecules by whether it was green or red spots. So the visualization was complicated, and then they went and looked at what you see. And this is what you find is you see the emergence of a pattern, as shown here. It's definitely spots, but it's not a regular pattern. It's not a regular deterministic pattern. It's a pattern that has emerged. It has a length scale, but it's disordered at the same time because of the noise. What is the noise in this case? Well, I've got stochastic gene expression. And because I've got stochastic gene expression, I've got variable numbers of the signaling molecules. Those numbers are small enough that those fluctuations are large, and they contribute to this pattern. Now, how do we know that the pattern is a stochastic Turing pattern? Well, we did a lot of analysis to work out the parameter range where you should be able to see regular Turing patterns or disordered Turing patterns. And we also worked out that because the patterns that are due to noise, they have a different kind of structure than if the system was periodic, like a crystal. And so when you look at the correlation functions as measured by the power spectrum, you find a different power law than you would guess if you had a regular Turing pattern, and you can prove how that emerges from the theory. So what we find then is that you can observe stochastic Turing patterns in a real system. So you have an emergent order, but now it's emergent and driven, stabilized in fact, by noise. Because without the noise, you wouldn't have the pattern. But it's not a regular pattern. It's a stochastic pattern. So here's the experiment, here's simulation, and they agree very well. All right, so I want to now, I'm going to skip this last one. I'm going to go straight to my conclusions, and then I will be happy to take questions. So what I've shown you is that emergence arises in large systems due to strong interactions between the constituents. I've shown you that there's a collective state emerges. It exhibits its own novel response characteristics. That's the emergent rigidity that we talked about. But that emergent rigidity means, and the emergence means, that you don't need to worry about what happens at the smallest levels of description. So in some sense, it's independent of it. It loses memory of the underlying physics, and that can be a good or a bad thing, depending on whether you want to find out what the underlying physics is, or whether you just want to understand it. The onset of emergence is usually accompanied by a phase transition and scaling phenomena, and it's accompanied by generalized rigidity, and that's really the important and useful thing. You can get patterns that emerge, and then when those patterns emerge, there are generic features of patterns, generic features of emergence, such as the existence of a topological defect. And then in the last example, I showed you that stochasticity can enhance emergence. What I didn't show you, because I want to take questions, is how we can exploit this emergence for purposes of modeling. Namely, if you have a very complicated system, I know that it doesn't matter what happens at the lower length scales, so I can make a simple model of that and use that to compute things that can be measured. Just like Kosterlitz and Fowler's did for their superfluids in 2 dimensions, but you can do for much more complicated systems, such as the example I was going to show you, which is the geophysical landscape. So with that, I think I will conclude, and I'll be happy to take questions.